Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on filter design. For this video, it's actually a B series. Earlier on, I have discussed how can we actually design a step impedance as a low pass filter. This video, I mainly will go through how can we actually convert the electrical length and also the impedance into the width and also the length of a microstrip line. So this will be the objective of this video. So again, if you want to see a complete discussion on the design of a step impedance low pass filter, please take a look on the A series 2. Okay, so this will be the part 23 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and also the subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Guys, once again, thank you so much for strong support. Let's do a very quick recall on the example. Okay, so the example actually tasks us to design a step impedance low pass filter that have a maximum flat response and they have a cutoff frequency at 2.5 GHz. It is also desired to have at least 20 dB of insertion loss at 4 GHz. The filter impedance, which means the input and output, is actually 50 ohm. The highest practical line impedance is 120 ohms, and the lowest impedance is actually 20 ohm. Okay, so we are also tasked to consider the effect of loss when this filter is implemented with a microstrip substrate having the microstrip thickness, the dielectric 0.158. So mu r is equals to 4.2. The tangent, so basically will be equals to 0.02, and the conductor thickness is actually 0.5 mu. Okay, so to be very frank, most of the time we only consider the thickness of the substrate and also the mu r. Okay, most of the time, all these we can neglect, because they don't play so-called very distinct role in determining the width and also the length of a microstrip line. This is what I have gone through on the A series. Okay, I actually stopped at to find the electrical length of both the high and low impedance, okay, which means that both the inductor and capacitor. Okay, so what I have did on the A series, I have actually successfully find the electrical length of the inductor and also the capacitor in terms of radian. Okay, so for this video, I'm going to show it to you how can we actually convert the radian to degree. Typically, this task can be done using your calculator. Okay, but I think nowadays we can also make the process easier. So I actually have included the link over here. So over this link, okay, allow us to convert the radian to degree. And let's take a look how this can be implemented. Now let me show it to you how you can actually convert the radian to degree. Okay, so nowadays there are lots of freeware you can actually do this. So if you do not know, okay, I will put the link under the description. If not, you can actually Google how to convert radian to degree, and you will actually pop up this. So basically, this will help you to convert whatever value that is in radian to degree. So earlier on, we have done this. Okay, so the radian, okay, for this case is 0.2068. So what I need to do is I just enter the value here, 0.2068. So you can see that it actually automatically convert them into degree. Okay, so the value is pretty close, 11.85. Okay, so basically this is how we can actually convert the radian to degree. Okay, so let me do another one, okay, which is the section 2. So basically will be the radian will be 0.589. Okay, so 0.589. So you can see that they actually convert into degree, okay, which is over here. So from here, you can easily convert all the electrical length of high and low, okay, which is the inductor and also the capacitor from radian to degree. So let's move on to the next step. Okay, let me continue. Okay, so basically this actually shows the transmission line of this step impedance low pass filter. So on the extreme left and also on the extreme right, okay, so this will be the input impedance, which is 50 ohm. So this will be the output impedance of the filter, which is also 50 ohm. The first section, okay, which will be a low, which means that it's a shunt capacitor. Okay, so earlier on, I have mentioned that the low basically can be 20 ohm, and I have actually so-called share with you how can I actually convert the radian into degree. Okay, so the objective now is basically how to obtain the W and L, the width and the length of a microstrip line. Okay, so basically I can actually relate this link over here in order to find the width and length of the microstrip line by having the impedance and also the electrical length. So let's take a look how can we actually do this. Okay, next, I'm going to show to you how can we actually, from the impedance and also the electrical length, how can we actually have the width and also the length of a microstrip line. Okay, before I actually do anything, okay, I need to fill out all this essential data for a microstrip line. Okay, for example, I need to know what will be the dielectric constant, what will be the dielectric height, and also the frequency. Okay, so from the question, okay, you can see that the dielectric constant is actually equals to 4.2. Okay, I can also obtain the dielectric height, okay, which is 0.158 centimeter, which I need to convert into millimeter. So therefore, it's 1.58. Okay, for this so-called microstrip, the utilized will be on a low pass filter. So I need to know the cutoff frequency of this low pass filter, which is at 2.5 gigahertz. So these are all the essential so-called parameters that you need to obtain before you can find the W and the L of the microstrip line. Okay, so now we are ready to find the width and length of a microstrip line. Okay, so this is actually the table. Okay, so I have actually shared with you earlier on how can we actually find the electrical length of the high and low, which is the inductor and capacitor. Okay, basically the degree. So I have this, and the impedance is basically also consists of low, high, low, high, low, high. Okay, so how can I actually find the W and L? Okay, so for this case here, let's do the section 1. Okay, for the section 1 is a low impedance. So I enter the impedance as 20. Okay, the electrical length must be in degree, so it's 11.85. So over here, I enter as 11.85. So once I ready, okay, I actually do this synthesize here. So give it some time. Okay, you can see that it successfully calculate the width and the length of a microstrip line. Okay, 11.26 something. Okay, quite decent, close to 11.3 here. So the length is 2.08. Okay, so it start off, okay, but definitely is still within so-called the acceptable range. So over here, okay, I have convert the impedance and also the electrical length into the width and length of a microstrip line. Okay, but before that, let me do another example. Okay, let's do the section 2. Okay, so the section 2, okay, the impedance is actually 120. So I change this to 120. The degree, okay, the electrical length in degree is 33.75. So let me change this to 33.75. Okay, so once I got all this again, I click on synthesize, okay, and the result will appear after some time. Okay, so you can see that the width is 0.43, okay, about the same. And the length is about 6.67, okay, which is definitely under the acceptable region. So from here, you can see how can I actually obtain the width and the length of a microstrip line. Basically, I need to have the impedance and also the electrical length in degree. So I enter into this format, okay, and then I will be able to obtain the W and L. Okay, don't worry, okay, I will include this link into the description so that you can also follow what I actually have been doing for this example. Okay, let's continue the discussion. Okay, once we have obtained the width and also the length of a microstrip line, okay, we can start to design the step impedance of the low pass filter. So this will be under the section 1. You can see that the width is actually 11.3 and the length is actually 2.05. This will be under section 2. Okay, so therefore the width is actually 0.428 and the length is actually 6.63 millimeter. So from here, you can have some idea how I actually continue to obtain the width and also the length for all these 6 parts of the step impedance low pass filter. Okay, so please note that I actually don't draw this to scale. Okay, it can be quite tedious. So basically, you can actually visualize from here. After we actually obtain the W and L, we can actually draw our layout, okay, with respect to the width and the length of the microstrip line. And once we done this, we are ready for this low pass filter. So once you simulate, okay, you actually can obtain this amplitude response. Okay, so this diagram here actually shows the amplitude response of the step impedance low pass filter. Okay, so let's focus on this. So basically with the dotted line and also the solid line. Okay, so the dotted line, okay, so will be the filter response, and basically the solid line is actually without the loss. Okay, the response of this also include the lump element. Okay, as you can see that the lump element actually has a steeper roll-off as compared to the step impedance low pass filter. So what will be the conclusion? Okay, the effect of loss is to increase the passband attenuation to about 1 dB at 2 GHz. So you can see over here, okay, you can see as I mentioned earlier on, okay, so basically with dotted line and also without, okay, basically the solid line is without any loss. So basically the solid line is without any loss. The dotted with loss, so you can see that, okay, at 2 GHz, okay, so basically is to achieve at least 1 dB. So this is what it means here. Okay, the effect of loss is to increase the passband attenuation to about 1 dB at 2 GHz, so as to ensure that we have reasonable so-called cutoff frequency. Okay, so basically this is what it means here. The response of the corresponding lump element is also shown in the figure which I have illustrated. Okay, the passband characteristics is similar to that of the step impedance filter. Okay, you can see that they actually look quite similar. Okay, but the lump element filter give more attenuation at high frequency, which means that they have a steeper roll-off factor. Okay, this is because the step impedance filter element departs significantly from the lump element value at higher frequency. Okay, so for this case, when we actually design for this step impedance filter, okay, at high frequency, because they are using distributed, and because of this, they actually deviate quite significantly. So please take note on this. Okay, the step impedance filter may have other passband at high frequency, okay, but the response will not be perfectly periodic because the line are not compensated. Okay, so with this, I end my discussion. Again, if you find this video helpful, okay, please help to like this video and also subscribe to this channel. Okay, once again, guys, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you so much.